Okay, in this video, we are going to talk about the comparison test for determining convergence or divergence of infinite series. So far, we've already talked about geometric series, p-series. We've talked about the nth term test, and we've talked about the integral test. So we're just going to add one more to our arsenal of tests, okay? And that is the comparison test. All right, so what is the comparison test? Given two positive term series. So let's say we are given one series with nth term a sub n and one series with nth term b sub n, and they are positive term series. Okay, so the comparison test is pretty logical. Let me write down the two rules, and then we will discuss them and do some examples. So, rule number one. If series of nth term b sub n converges and b sub n is greater than or equal to a sub n for all n, then series a sub n converges. And this just makes logical sense. You have a series that you know converges. So if I add up all the terms in the series of b sub n, they converge. Well, then if I have another series where all of the terms in this series are smaller than the terms in that series, well, then it obviously makes sense then that this series must also converge. Okay, so then the corollary to that would be if the series of b sub n diverges and every a sub n term is greater than every b sub n term for all n, then the series a sub n must also diverge. And again, this makes sense. I have a series that diverges. I have another series in which every single term is bigger than each term in my given series. Well, if this diverges, this must also then diverge. Okay, so let's do a few examples. So let's start with the series from 1 to infinity of 1 over 2 plus 3 to the n. Now, 1 over 2 plus 3 to the n does not fall into any of the categories of series, specific categories, geometric or p-series, that we've already tested. And I can quickly look at that and see that if I do the nth term test, if I take the limit as n approaches infinity of 1 over 2 plus 3 to the n, I'm going to get 0, which is inconclusive. So now I am going to use a comparison test. Now, this looks a lot like 1 over 3 to the n. Well, and I know that 1 over 3 to the n, well, that's the same thing as 1/3 to the n, right? This is a geometric series. And in this geometric series, r is 1/3, which is less than 1. Therefore, this series is convergent. Well, I know that 1 over 2 plus 3 to the n is less than 1 over 3 to the n for n is greater than or equal to 1. And I can prove this. Think about giving these a common denominator. 3 to the n is less than 2 plus 3n, or comparing their denominators would be another way to look at this. 0 is less than 2. So that confirms that for all terms n is greater than or equal to 1, 1 over 2 plus 3 to the n is less than 1 over 3 to the n. Well, therefore, from that, I can then say, well, then that means that the sum of this series, 1 over 2 plus 3 to the n, must be less than the sum of this series, 1 over 3 to the n. And since I already proved that this series is convergent because it's a geometric series with r is 1, then I'm going to say that the series from 1 to infinity of 1 over 2 plus 3 to the n converges by comparison test to this geometric series. Where, as I stated earlier, r is 1/3, which is less than 1. Okay, let's look at another one that you saw in your homework last night. Okay, and in the homework last night we saw page 721, number 36. You showed that the nth term test was inconclusive for the series from 1 to infinity of e to the n plus 1. The nth term test, we did the nth term test. The limit as n approaches infinity is 0, which means this is inconclusive. So I'm going to give this a name so I don't have to keep writing out my equation. Let's call that the series of b sub n. And then I'm going to say, let's let the series a sub n be the series from 1 to infinity of 1 over e to the n, which is the series from n to infinity of 1 over e to the n. And this is a geometric series r is 1 over e, which is less than 1. Therefore, this series is convergent. And then I'm going to say 1 over e to the n plus 1 is less than 1 over e to the n for all n greater than or equal to 1, because e to the n is less than e to the n plus 1, or 0 is less than 1. So that meets the criteria that I need to apply the comparison test. So I said that my conclusion would be that B sub n is less than or equal to A sub n for n is greater than or equal to 1. Okay, so we are going to determine convergence for the infinite series from 1 to infinity of 3 over root n minus 1. Okay, so again, this doesn't fall into any of the categories that we've talked about. I'm going to call this A sub n, and I'm going to say let's compare this to the infinite series from 1 to infinity of 1 over root n, which I'm going to call that B sub n when I write my conclusion statement. Okay, so we know that for this series that I'm comparing to, this is a P series, okay? And in this P series, I have that P is 1/2, which is less than or equal to 1. Therefore, this P series is divergent. Okay, so really what we're saying is that we cannot find a sum for this P series, that this P series must add up to infinity. So if I want to use the comparison test, I need to show that these terms are bigger than these terms. And that, therefore, if this adds up to infinity, this must also add up to infinity or be divergent. So let's compare their terms and see if we can draw that conclusion. I want to say that 3 over root n minus 1 is greater than or equal to 1 over root n. Okay, so I'm going to give them a common denominator. If I give them a common denominator, I'm going to multiply by this by root n over root n. And so I would have 3 root n in the numerator. And I would have over here, multiply by root n minus 1 over root n minus 1. I would have root n minus 1 in the numerator. And so now I'm going to say that this is 2 root n is greater than or equal to negative 1. And I'm going to square both sides. And, well, I don't even need to square both sides. I can just justify what I have here. If this is true for any positive value of n, and that meets the criteria that I was looking for. So I now know that series A sub n must be greater than or equal to series B sub n for n is greater than or equal to 1. So my conclusion then is, by comparison test, to divergent series 1 over root n from 1 to infinity, the series from 1 to infinity of 3 over root n minus 1 must also diverge. All right, and that is the comparison test.